All right, let's get started. I think the audio is working. Yeah. Welcome to week 17 of Hobby OS Dev kernel development, which is where I embarrass myself live on the internet as I attempt to learn about kernel development. And I'll just also say that if you're watching the video recording, I would recommend just watching like probably the last 10 minutes or less of the stream because usually that's kind of when the good stuff happens. Yeah, we've been working on the physical memory allocator today, and I'm going through this memory management lab. I'm just going to post a quick hello in the chat like usual to kick things off. Yeah, so I've been working on this physical memory allocator, and it went pretty well last week, and we're just going to keep that up this time, just kind of going through exercise 1. And I think, yeah, without too much further ado, I will just get into it. Let me quickly prepare my terminal in case there was any embarrassing stuff I did not want to show immediately. No, I think I'm good though. Okay, yeah, just coming back to this. This was where I was working last time. Clean working directory, had my debugger setup going. I think I can close some of these panes. Let's just totally reset. Make clean, make Kimu. And this is where we expect it to be. It's we got some printouts for the debugging we were doing for the physical memory allocator. And we're going to keep that up. All right, where were we? So I think pmap.c did boot alloc last time. Mem init was important. And then we had just initialized this page manager. I'm just going to take it to do. Actually, one thing one kind of shower thought I had this past week was this comment. It's saying, page init, after this is done, never use the boot alloc again. And I had just wondered if it would be possible to make some kind of assertion to actually encode that requirement in code rather than a comment. Something along the lines of the boot, like after we initialize this page allocator, we change some state about the boot allocator such that if the boot allocator is ever used again, it asserts. I'm just going to make a quick comment about that. Can we add an assert to boot alloc to enforce this? Yeah, so just real quick, that's what I'll just do. Add to do route boot alloc assert. Okay. But yeah, let's keep it moving. Let's just get right into it. So I just made the page init work last time. The code's kind of garbage, but I decided to kind of change my philosophy around how I'm doing this, where I'm more focused on working on the actual core content that matters to me in the core learning. And I'm, for the moment, not so worried about code quality because my intention is that I am going to eventually like totally rewrite all of this from scratch. Now that I've kind of done it in a bit of an easier kind of introductory environment. using this like class, this MIT class. So I'm not worried about code quality at the moment. It's kind of gross. It's extremely gross. I mean, these names are kind of weird. One thing I just realized that I kind of totally named wrong last time. I mean, it's also a little bit weird that these things all start with K if they're not if they're like kind of computed and not really compile time constants. I've just seen the K pattern used before. It's also weird that this thing is named with K because it gets initialized at runtime. So I think I want to just do one of these renames. It's like G pages or something, just to make it clear that this is a global variable. I hope that still compiles. I think it does, yeah. Okay. G pages. Let's just read through the lab one more time. So you must implement code for the following functions: boot alloc done, page init done, page alloc. I did not do that. So page alloc is next. Let's get to it. Okay. Also, as a quick recap, we're writing a physical memory page allocator. They call it page allocator. For me, the word frame is a little bit, that's more what I think of when I think of physical memory. And the whole point of this was to create a data structure that represents physical memory and represents all of the free pages or frames that are eligible to be used in the allocator. And the important part is that not everything was eligible. There's a bunch of these like random holes and little parts of the physical memory space which are not considered eligible because stuff lives there. Like the first page, there's like, I don't know, the legacy interrupted vector table or something like that is like maybe still there. This was all explained in the comment here. Yeah, real mode interrupted vector table. That's a typo. They should have said IVT, I think. Some BIOS stuff. That's all free. Then the IO hole of like whatever. I think video memory is there. And then, anyway, and then the kernel, and the space that our kernel is currently using is not free. And so we've generated this data structure, which is like models physical memory with one like object per frame. And then we've gone through each of these and constructed a linked list of all the free ones. And that's literally all we've done so far. So now time to read, check the physical, oh, oops. So now I need to implement page alloc, which I have not seen before. So this is my first time seeing this. And I'll just read through it. Allocate a physical page. If alloc flags, okay. You can pass some flags, fills the entire with 0 bytes, does not increment the ref count. The caller must do this if necessary. Interesting. Be sure to set the pp link field of the allocated page to null. So page free can check for double free bugs. Turns null if out of memory. Hint, use page to KVA. Okay, what is page to KVA? Page to kernel virtual address, probably. Also, why did, oh, my symbol finder. Okay, yeah. There's different keyword shortcuts. There's like Command T for the global one, and then Command-Shift-O for the one local to the current file. And realistically, I should be using Command-T all the time because this project is so small that finding the symbols won't be a problem. What does this do? Page infos. So page infos are struct from last time. It's like this like object that represents each physical frame. It doesn't really have any data other than a ref count. Like that's like almost literally it. The linked list thing is like a little bit irrelevant to the actual object. It's more for the metadata of the container we're trying to store it in. So it's like an intrusive linked list. And it's page to, so first of all, we have a page, so page to PA. So first off, this is kind of what I was doing last time. I was messing up virtual address and physical addresses. So the way we can convert from one of these page objects to the actual physical address it corresponds to is by subtracting against the start of G pages, right? Because we have all of these elements, and if we can get the index, like basically index 0 corresponds to physical address 0. Index 1 corresponds to physical address 1 page. So first, the idea is to get the index into this array by subtracting against, so taking the pointer to one of these and subtracting against the start. And then you have the frame number, and then you convert that, you do the last step of converting that to an actual physical address by applying the page shift. That makes sense to me. And then converting that to a kernel virtual address. Interesting. I don't actually, not totally getting that actually. Physical address returns the corresponding kernel virtual address. It panics if you pass an invalid physical address, and it's a macro for some reason because of the panic, I guess. Oh my gosh. The function. Wow. It's kind of interesting though. Yeah, the goal is to provide a, it's so strange to be passing in a file name and a line into this like core, to this like kernel API, just so we can pass it to the panic function. Like ideally, like assert should be used here or something, not this weird panic thing. Anyway, physical address T, which is what again? That's just a type def. Okay, good to know. Also, wow, we manually define uint pointer T. We don't get that for free or something. That is interesting. I didn't know that actually. Apparently we are in such a minimal C environment that we don't even have. I guess that kind of makes sense. Like we don't have any standard library or anything. We're like, this is like quite raw code, and I guess my understanding is that these types usually come from like some standard library headers, like int types or something like that, but I don't really know. Anyway, phys address T, so just for a semantic distinction, we have a different type for that. I guess that's kind of cool. Although there's not really any type safety because it's all just uint 32Ts at the end of the day with type defs. And then we just add kern base. And let me understand that for 1 second. Excuse me. Okay, so it's super handy to have our physical, our memory layout diagram. So given an arbitrary kernel for physical, given a pointer or a physical address that corresponds to some range the kernel, we can convert that to the kernel virtual address by adding the kernel base offset and to get this region, which is where the kernel is. But this only works, it's like, doesn't work for everything. It works only for the kernel, like literally, so our page tables right now only map a 4 megabyte region from kernel base. And so this only works for any physical address that's also in the first 4 megabytes. Yep. Yeah. Okay. Okay. I'm going to keep it moving. 1 second, just checking that the stream is going okay. All right. Nice. Yeah. Back to this. That is interesting that it uses flags. I don't know, it's like a C API kind of thing where rather than passing a bunch of bools or something, you pass the flags. Whatever. Okay. Allocate meaning what? What do we return? We return a struct page info. So presumably, let's go back to this. So let's say this is how our thing looks. My first kind of like simple guess is that we just need to take the first thing off the page free list, and that's it. We need to this is going to be our candidate. That's the thing we're going to allocate and give away. Then we're going to need to point this thing over here. We also need to unlink this thing, I believe, like it said, to null. We want to unlink this. So this is kind of the state we want to end up with. If out of free memory. Okay, time. Let me see if I can do some coding here. So first off, returns null if out of free memory. What does that mean? Out of free memory means that we don't even have one page. This thing points at null. We're out of memory. So let's start with the easy case. If page free list equals null, return null. Yeah, I'm pretty confident that's right. Wait, what says return 0? But that's like garbage, right? That's not real. Okay. Now let me undo this. So we need to so struct page info. I'm just gonna say the name of this variable is something like the selected or available page equals page free list. Page pp no, it says not to touch that. Link equals null page free list. Oh wait, but yeah, I'm kind of dumb. Okay, page free list equals pp link. Right, we can't throw away the link. We need to use it before. So get the top of the list. Yeah, get this pointer. Reset this thing to the next, right? And then set pp link to null. And then return available page. Maybe instead of available, I'll say free page. Okay. Free page. I think that's okay. That's like roughly a very basic version of this. And let's just see if it compiles. Pretty sure it should. Yep. And now I am going to implement this advanced feature where I fill the entire return with 0. Okay, so now how do we do this? That's going to be kind of like an optional thing here, I guess. So if alloc flags and alloc 0, then we're going to do some mem setting. In order to do the mem set, we're going to want to operate. 20-second break to stand up and stretch. Be right back. Right. Yeah, so in order to do our mem setting, I'm going to need to refer again to this thing. So what we have is the free page, which is a page info. And so like we just covered, we're going to want to convert that into a kernel virtual address. Actually, like low key, I think it would work to not go all the way to the kernel virtual address, because we, like low key, we do still have this low mapping that was only necessary for the transition from into paging mode. That was the thing, just to recap, that was the thing we saw here. So this code runs in low memory, because paging is not enabled yet, but now we enabled it. And in order for this instruction, I think it's literally in order for this instructions to run, these instructions, we needed to have this little mapping of the low 4 megabytes to still work, basically. And then we immediately relocate and start executing up in high memory, which is where we want to live. But for the rest of the kernel so far, we've never gotten rid of that. So technically, and it would not be good form, but we could actually just continue to operate on these low addresses because they are still mapped. And that might be an interesting test to test our knowledge later, but for the moment, I'm going to do things the right way. And which is going to be, it's a void pointer. It's page VA. So, yeah, like naming is always tricky. Equals page 2 kVA free page, right? Please tell me that's right. And then what? Memset free page VA 0 page size. Okay, I think that's like roughly what I need to do for this function. And I could, now maybe time to read what the checker function even asks for. Wow, that's kind of long, okay. Oh, but I'm not ready yet because I didn't implement page free. Okay. So I guess I'm just gonna blindly keep going because I don't really know how I could test this code. One of my future ambitions is to make this all unit testable, which I do believe is totally possible. I think there's this, I think some people have like this opinion that kernel code cannot be unit tested because it's so close to the hardware or something like this. But, and maybe they're right because I don't have that much experience, but I have this belief that there are definitely ways to use software engineering principles to like mock things that touch the hardware, and I think it would be possible to unit test this. Absolutely. I just I think it would take quite a bit of restructuring of the code because there's so much currently, like right now there's so much global state used. It's like literally everything is global variables, which is not conducive to unit testing. Yo, Lus33R, thanks very much for the kind comment. Thanks for being here. Appreciate that. Yeah, so in the absence of being able to unit test this, I think I'll just keep going and hope that it's correct. Like I do kind of, oh yeah, what? I could add some client code that tries to use this and just do some basic verification of that, but I think that would slow me down a bit too much. I'm kind of trying to move, I want to move a bit faster with the stream. I think last time I was really a bit overly conservative, and I think I can move a bit faster. Return a page to the free list. Only be called when ref count reaches 0. You may want to panic if it's non-zero. All right, I'll take that hint. Isn't assert the function though? Can't I just, isn't that like way better? We do have an assert, right? Yeah. Yeah, we should be using that everywhere. We should not be manually panicking, I feel like. Okay. But I cannot provide yeah, okay, great. Assert pp count equals not 0. And by the way, for anyone watching, like, please feel free to ask any questions. I'm very happy to answer stuff if things are not clear, because it also helps me understand things better also. Hey, nice Nick, thank you. Did I consider C++? I definitely want to eventually move to C++. Right now, like, I'm working with this MIT operating systems class learning OS, so I didn't write a lot of this code, but personally I'm way more comfortable with C++, and I definitely want to move towards it. And yeah, when the time is right. But it is kind of nice, although, because I use C++ every day at my job, it is kind of nice to just use C and just have so much less surface area of the language to worry about. So it is kind of nice getting a bit of a break from C++ and just getting a chance to kind of refresh on what life is like as a C programmer. Panic or is not null. Wait a sec. Okay, so yeah, this is that thing they said last time to do. You know, in the earlier function, the idea is we need to make sure to set the link to null. So therefore we can do these assertions later on, I think. Yeah, so now we're implementing that. Now it says return a page to the free list. This function should only be called when it reaches 0. So therefore we can assert it. And so therefore we can confidently proceed with that. And let's kind of, so I mean, actually, no. So let's say this is the state of our allocator. And it's time to return a page to the list. Return an arbitrary page info. Okay, yeah. So this should not be that hard. Let's just say, as an example, yeah, this is the one that's being freed. Or yeah, being freed. We need to, what do we need to do? We need to do sort of like the inverse of what we just did. Like this thing, we basically add it to the top of the list. I think that's the easiest thing to do. So this thing now points back to the start. And this thing now points to it. And we've kind of repaired the list. Let's give that a try. P link equals, oh shit. No, pages free, page free list equals pp, right? That's what I just did. So, no, I think, yeah. pp link ref equals pages free list. Wait, yeah, no, I'm getting a bit confused. Yeah, this thing points here. This thing now points to here. And then pages free list points to pp. Why am I getting a oops. Is that easy? Right? We have some list state. We don't need to keep this like in this perfectly kind of ordered thing like we had at the start. So there's no need to do anything too fancy. Just like point this to the start of the list and reset it. Yeah, point and reset it. I'm gonna call that good. Let's see if it builds. Okay, is that it now? I'm just gonna go and test it out. So now let's see if I did this right. We're gonna execute check page alloc. I mean, maybe I'll just read it to see what it is. So it's going to do some it's going to do some consistency checks on the list. So first off, G pages, non-null, gotta be non-null. Then get all of them. Should be able to allocate 3 pages. I could actually step through. I'm gonna do that. I'm gonna do that just for fun. Make new GDB. Make GDB. Break check page. What's it? Check page. Check page. Alloc. Continue. We're there. Nice, Nick. I started the OSDev journey with C. I realized I write actually OOP code. Currently I use C++ just for classes, namespaces, auto, and pointers. Yeah, that's exactly what I'm thinking too. I love that because I'm a big fan of OOP in just like the simplest sense of having like objects. I'm not talking about like inheritance or stuff like that, just having like the abstraction of an object where you have like data and code that's kind of co-located and operates as a unit. And so, yeah, I think ideally if I were to be writing really idiomatic C, I would do exactly that same thing, but then it always ends up so verbose because all your what would be like methods need to be free functions with just like the prefix of kind of like the class name. So all your like function names get very verbose. You need to manually pass in like the this pointer all the time. So I would do the same thing. Yeah, I would like, for me, C++ is just like what I want to use is just like classes, maybe some basic templates, but that's not even really the main thing. Like static assert. Like I like the different kinds of casts also. So there's static assert, but then also like static cast, reinterpret cast. I think those are really nifty. Some smart pointers can be useful too with like templates and stuff, but yeah, it's also, I just like, I don't really know how to set up the more advanced features like exceptions. I wouldn't know how to set that up for the kernel, and so I wouldn't even be able to use that anyway. But that's cool. It sounds like you have your own OS that you're working on. That's awesome. Would love to hear more about it. Okay, G pages. Oh, this is gonna like run a million times. Can I break on pmap.c 611, I think. Okay. Let me just read this though. So we should be able to, that's so funny, sets them all to 0, allocate 3 things and assert that they are non-zero. And assert that they are different from each other, and assert that the physical addresses are all less than physical memory. That's funny. End pages is all our physical memory. Page sizes, this like converts it into like the actual top of physical memory. So these things need to be within physical memory. That's kind of funny. Temporarily stealing the rest of the free pages. Ah, interesting. Should be no more memory. Free and allocate. So then we, but wait a sec. Interesting, okay. Then we free 3 pages. Do 3 more allocations and do the same test where they should be different. Oh, page alloc 0. Did I handle that? I'm not sure I actually handled that. Oh, wait a sec. That's just 0. Okay. I didn't realize that. Okay. And then test flag. Okay, now it's, okay, so what is that doing actually? It just allocates another thing, but like kind of leaks it because he doesn't get this, doesn't store that memset, and then they memset this thing to 1, free it, ask for it back, check that it's the same, and then manually for every single byte assert that it's 0. That's, yeah, it's kind of interesting. I wouldn't, how is there a better way to do that? I'm not, yeah, no, not sure. Give those back. Number of pages should be the same. Okay, I'm just gonna run it. Screw it. Okay, I have a bug. Damn. Huh. Assertion failed. 380. What happened? I mean, yo, the Roy 714. Hey, what's up? Thanks for joining. Great to have you. So clearly I have a bug. So somehow PP were freeing something that didn't have the, What I want to do is trap into the debugger though. That would be so cool if I could like run it in the debugger. I mean, I like obviously, well, wait. Can I even I cannot set a breakpoint in the assertion function because it's a macro. Because it's not a function. In user space, I would do something like built-in trap, but I don't actually know what I would do in kernel, like to do this in the kernel. That is too bad. Macro debugging is a pain. Yep. Hey, LS mail. All right, 20-second break. Okay. Serious question though. What do I do now? I mean, there has to be some function I can break in panic, I guess. Yeah. Panic is a real function. So that's my answer. I can just break in panic. Okay. Because then I can hopefully get a stack trace. Oh no. Okay. Panic. Continue. BT. Also, why is everything optimized out? Why am I using optimizations? Why? I need to not be doing that. How would I see flags? Huh. So O1 was originally used here because there was some like lab exercise for building a stack trace. which I'm no longer doing. So I am going to get rid of that because it's kind of annoying to it's like annoying to have things be optimized out while I'm in such like an early stage of this. Did I do something wrong? Oh, wait, what's going on? What happened? Did I do something wrong there? Oh. Okay, I think I know kind of what's wrong. Now it's actually trying to execute my my backtrace function, which is not prepared to handle. Oh wait, but what? Oh wait, no, is it? Is it? Okay, I disabled optimizations. Or it, Oh, 0. Do I even need that? Yeah, 0, right? Okay, so there should be no optimizations. Okay, that's I was just trying to find out what is going on. There's some infinite loop. I don't even know, but I don't know where. It's very strange that very strange. Okay, just to test, if I add this back, does it work again? Yeah. It's just it breaks if I disable optimizations, which is the strangest thing. I cannot think of a good reason. Well, getting rid of macros is maybe another reason to switch to C++ in the long term. Yeah, definitely. I mean, yeah, I think you still could benefit from some macros in C++, for example, for assertions, which you really want to get inlined into the function frames. But yeah, you can avoid a lot of them with templates in C++. Okay, I kind of don't want to debug this right now. It's a very weird and strange bummer that disabling optimizations, which I was trying to do because it would make my debugging experience better, breaks the kernel. So I'm gonna pretend I didn't see that, and I'm just gonna see if I can debug this with optimizations turned on. Wait a sec. I feel like I just did something kind of weird. Okay, I ran that wrong. GDB. The most important part is the line numbers, I suppose. Kern pmap.c. Okay, well, what happened? I am having this assertion fail, and it looks like this, which I will just capture for reference so I can look at it. Okay. Assertion, oh, jeez. Is this even, am I correct? Oh wait, no, I'm stupid. I inverted, that was dumb. I got the assertion wrong. It should be equal to 0. I'm stupid. All right. Okay. Well, time for the next one. PP. Did I also mess this up too? It should be equal. Yeah. Yep. I think I actually just literally got both of those wrong. Okay. Yeah. That was it. Yep. That's kind of funny. Check page alloc succeeded. Wow. I wrote all of the actual code right, but I messed up the 2 assertions in the program. Okay, well, moving on. A bit embarrassing. How do I go? Yeah. Okay. Yeah, I literally got all this code right. I mean, it's not that much code, but like on the first try, and I just messed up the assertions. I'm just going to commit this. Okay, nice. Let's. Okay, are there any other asserts I could add, though? That's a great question. I mean, this is all kind of... For example, what asserts would I add to page init? I'd probably assert that this thing it's like allocated at the end, although... That feels a little bit silly to me. Like, to me, that feels more like the role of unit tests. Although, I mean, asserts only help unit tests be more effective, I feel like. So, yeah, why not? Page free list. I don't know. Maybe that's kind of dumb. I'm not actually super convinced by that. What assertions could I check here? So allocating the page, returning this thing. For example, like we could assert that this thing sets it to null, but that's not, I don't know. I mean, that is kind of an invariant we want to enforce. What about the reference count. Do not increment. It should be 0. So I'm just kind of wondering who. The caller of this apparently is responsible for modifying the ref count and incrementing it. What about decrementing it? Is the caller also responsible? I guess so. I think I'm not going to think about this more. I'm just going to move on. What does check page do? Okay, so now we are getting into part 2, virtual memory. This sounds kind of hardcore. Familiar yourself with x86 protected mode, segmentation, and page translation. Maybe a good time to open up the Intel manual just in case we need it. Let me just do that. LS mail, yeah. I am, yeah, kind of. This is a class, actually. This is like MIT's operating systems class. And I'm following the one from like 16 years ago, apparently. Is that right? Yeah, no. Yeah, something like that. Yeah, I'm just following along. It's kind of a tutorial, but it's much, I mean, it's not a tutorial because I have to like actually like, it doesn't give you the answers. It's not like a how-to, but they give you a lot of stuff, which is really nice. And for me, it saves me a lot of time to not have to set up a lot of the basic infrastructure. And then eventually I can do that when I'm skilled. But for the moment, I'm not that skilled. Segmentation, page translation. How segmentation works in protected mode to understand what's going on with JAWS. Okay. Yeah, it is very nice that they do this. Blah, 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 blah. Whatever. I think I understand mostly this stuff. Just kernel. You have to write the code yourself. Yeah. I mean, it's like a step-by-step thing. If you're not ready for this, then there's definitely other things you are ready for. You just need to figure out what they are. Like probably learning, I wouldn't advise learning C at the same time as learning operating systems because it's kind of a lot of concepts. So don't learn at once. And so, but once you do know C, I think, and are pretty confident with it, you could start to learn and like read some of this stuff. Also, this what I'm doing right now is only the second half of the OS class. The first half is just kind of like reading and learning this other one called XV6, which is like, it's like kind of like done-ish, and you just kind of like read it from what I understand. You don't like modify it too much. So okay. Consistently. You cast visions, 2-pointer, you can. Okay, Nick, nice Nick. No, it is not. Mostly because I have not like written like a lot of code for it. Basically, if you want to find the kernel that I'm using, it's like the link is on this MIT page. and they have a Git thing you can download. Oops. But I haven't really felt comfortable or like the urge to put it on GitHub or whatever. I think I got it from here, Git clone. Yeah. Maybe someday. But I'm a bit too embarrassed at it for the moment. Okay, let's just answer this question. Assuming the following JAWS code, what type should variable x have? Mystery T. X is some type of variable. We get a character pointer. We set it to 10 for some reason. And then we cast x to it. Value is a pointer. I mean, I think it's uint pointer t. Whenever we're operating in like code, like C code, for the most part, it's going to be uint. Well, I'm pretty sure it's uint pointer t. Is there an answer? Okay, I don't know I don't know if there's an answer. I'm pretty sure. I'm like, I don't know why it would be phys t. Okay, bootloader sets up. So the kernel runs at this thing. Yeah, I think so too. Yep. Even though it is actually loaded. But it's linear. So wait a sec. So physical address is like 1 megabyte. The virtual address is up there, but the linear address okay, 20-second break. Okay. The linear and physical addresses are the same because we're not enabled paging translation. There's like some diagram of this in the manual, which like I kind of just want to, or I think it's in the paging section. Love that diagram. Okay. I see. Basic VGA driver. I have the one that kind of like came with the OS. Yeah. So I have like this basic thing working, but I didn't really write it. I think there's like some nice diagram where it clarifies physical versus linear versus, yeah, here it is. Logical address in protected mode, linear address, physical address. And like right now, yeah, there's no paging, so these are one-to-one. So linear is basically the same thing as physical addresses. Yeah, Nick, out of curiosity, is your OS on GitHub at all? And yeah, just in general, like, yeah, like where are you on the path? We're going to stop using page translation. Okay, the point of this paragraph is like, okay, we have physical memory. We currently have, yeah, physical and linear map one-to-one because we don't have any paging. Wait a sec. Wait, what? Wait, is that true? Wait, what? Well, we kind of have paging. We do have, we literally do have some paging. I'm actually a bit confused by that because we actually do have paging enabled right now. So now that I look at that again, I'm not quite convinced by it. I'm not quite sure about that, but whatever. I'll just keep moving. After you finish the lab, and kernel enables paging, linear access will be the same as rather than being as same as the physical addresses. The R1, the bootloader, first enters. Okay. He has to read or modify for which it only knows the physical address. Require adding a mapping to a page table may require allocating physical memory to store a page directory and then initializing that memory. However, the kernel cannot directly. The key point being initializing that memory, like writing it to that physical memory. But you can't directly do that, so then you need to always map. For one reason, maps all of physical memory starting at. Maps all of physical memory. Okay, I think the hidden asterisk here is that there isn't that much physical memory which allows this to happen, because there's only, I think, what was it, 256 megabytes. I think there's only 256 megabytes of memory up there. So this only works if you have 256 megabytes or less of physical memory, which currently is the case. We have 128 because that's the default from QEMU, but I think that's just one important thing to know here. Okay, to find the physical address. Okay, physical address in memory in which virtual address space pointers type uint pointer t. Not quite. Uint pointer t is the type you use when you have a virtual address and then you want to operate on it mathematically, like shift bits or like and in or bits into it. But that's mostly the only time you use uint pointer t. Virtual address space pointers in general, for most of our purposes, almost all of the addresses we're going to be dealing with are going to be virtual addresses, except for very specific situations, I think, like touching hardware, stuff like that. maybe time to just like stop reading and like just try to write some code and see where I fail. Manage page tables, insert and remove linear to physical mappings. And to create page tables when needed in future environments, you will often map same page on multiple virtual addresses or in the address spaces of multiple environments. So you will keep a rough count, the number of references to the physical page in the page table below utop. I don't know what utop is. Mappings of utop are mostly just set up at boot time. Utop, okay. When the count goes to 0, the physical page can be freed. What is utop? I think that's important to understand, and I don't. Oh wait, I think I see. Okay, utop is like some specific detail to the way we're going to lay out the kernel virtual address space. I think it's not that important to understand right now, so I'm gonna ignore it. Okay, let's keep, so yeah, you must implement code for the following functions: pagedir walk, blah, 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 page check. Okay, let's just, yeah, pagedir walk. But what is the goal? Wait. So routines to manage page tables, insert and remove linear to physical mappings, and create page tables. And yeah, for some reason we need to walk. Okay. Given pagedir, a pointer to a page directory, pagedir walk returns a pointer to the page table entry for linear address VA. This requires walking the 2-level page table structure. Just to recap that, I think yeah, this is the diagram we are interested in. It's pretty simple. And I think, as I was saying before, it's a little bit, I think this diagram makes it like more complicated than it needs to be. But like the part I've highlighted in red are the actual like data structures. This thing on the right is just memory. Like that's not a data structure. Hey Brar, I just started learning Java. Please help me. How can I learn programming like you? I think it's important to take it step by step and follow what interests you. So yeah. If you want to learn like systems programming, then you want to learn a systems programming language, probably. Like C is a very common one. That's the classical language to learn. But also, not everyone is ready for C immediately, because I think so. Maybe learning some Java and then moving to C and then learning some OS concepts is like a progression you can work with. Thanks for the question, though. Yeah. So when it talks about 2-level structure, this is the literal 2 levels that we're talking about. 1 level for the page directory, which can map a 4 megabyte region. 1 level for the page tables. Okay. The relevant page table might not exist yet. This is true, and create equals false, then pager walk returns null. Yeah, everyone has their own path. Yeah. And I also think another important thing is to make sure to have fun somehow. Like find projects that are fun to you, because these things take a long time. And if you're not having fun, you're not going to stay with it for the time it takes. Yeah. Okay. And okay, if it doesn't exist and we're not creating it, return null. Otherwise, allocate a new one with page alloc. That one fails, then return null. Otherwise, the new page's reference count is incremented. The page is cleared, and page.walk returns a pointer into the new page table. What? Pointer into at the page table entry. Okay. Save to leave permissions in the page. Oh, what? I'm gonna use text permission bits in both. So it's safe to leave permissions in the page. They're more permissive than strictly necessary. So that, I think I know what that means. There's like permission bits inside the page table entry, but also in the page directory. For example, if the entire 4 megabyte region is going to be not like read only, for example, I think you can just set, well, I don't know, but wait a sec. Or you can set it to like be like non-writable or something. Okay, but if like access is disallowed by the page directory, then I think the CPU automatically just like quickly stops there, which is more of an optimized case. But if something is allowed in the page directory and then is disallowed in the page table, then it will also enforce that. So, yeah, I think I'm at like maybe like 80% understanding of that. Like it's not completely there, but I think I could find out if I needed to. For macros that manipulate. Okay, let's do this. Okay, so now we're going to, but also wait a sec. There's only one page directory, right? It's kind of like what I thought, because let me just do some basic math. Just curious. So 4 times 512, 2048 megabytes. I did that because I thought it was like 4 megabytes per page directory, and I thought there was 512 entries. I was just trying to get an intuition of like, I had this intuition that we should be able to like map 4 gigabytes like with 32 bits here. But I'm pretty sure this means there's one page directory and then just a bunch of entries. But there's 10 bits of entries. So is that how you do that? 2 to the 10? That was 1024. That makes sense. So that would make sense, yeah. So it's like 4 megabytes times 10, 24. We've 4096 megabytes, which I'm pretty sure is 4 gigabytes. Yeah, I'm pretty sure. Okay. Anyway, what's the first die? So So I'm going to break this into a couple of different levels for myself. So basic version, I don't know. There's a bunch of different things I need to do here, and I feel like I can do them in various, like what's the easiest thing? Like I usually kind of handle these error checking things a little bit, but okay, basically what we need to do, we have a pointer to the page directory. We need to like deconstruct the virtual address to get all these indices that we need. And luckily they have all these macros. Okay, luckily we have all these macros that are very helpful. So I'm just gonna that's kind of the first step, is just unpacking all the stuff we need from the virtual address. We need the directory index, we need the table index, we need the offset. I mean, we might not need the offset, but I'm just gonna call it int dir index. Dir entry index equals pdx, I guess. Okay, maybe, I mean, yeah. Eventually, I would want to get practice writing these myself too, but maybe that's for later. And what are we doing here? We are, I mean, what? Maybe I should just not look at this. Like, maybe I should just do that myself. I kind of want to. Like, that's kind of like the whole point of why I'm doing this, is to learn this stuff. So I am going to try to ignore that and like make it scroll off the screen. Okay, I'm gonna make my own macros. And just see how that goes. Page dir. No, yeah. Page dir index. LA for logical address. And we need to shift this thing down like a lot of bits and then extract out just this part. But it's time for a 20-second break. Okay. So I feel like we want to shift this thing down. Is it 22 bits actually? I am pretty sure. So like this number is like the bit index. There's definitely 12 bits in the offset because you need 12 bits to represent every offset into a 4K page. And so I think the number to look at is like the one like here. So I am just going to start off with this, and that's obviously not enough. And then now, well, wait a sec. Is that not enough though? Because this thing is only 32 bits. And so if we shift it by 22 bits, I feel like that's all we want. Okay, I'm gonna look at the answer. Page, what is this? 22, right? So I guess, but then it masks it by 3FF. which is what? I think that's 10, which is 10 bits. Yeah. I mean, I don't know why I just did that. It's kind of, I'm not going to count this thing. FF is 8 bits. Hex 3. 3 is 1, 0. Yeah, but like, I don't think that's necessary. I think that's kind of unnecessary. And maybe I'll run into issues later with that, but oh wait, okay, they have the diagram right here. Like why, like the reason you would mask it is because you would think there's other stuff over here that you need to zero out, but there isn't, I think. Decompose linear addresses as shown. To construct a linear address, use page adder. Okay. For example, now I'm going to do my page table index, which now means I'm going to shift it 12 bits over. And then now, now I actually want to mask it by 10, because now we are only shifting it 12, then we want to extract just this part. Page set. And then here, we're just going to want to mask it. What's the number? Yeah, right? Pretty sure that's right. It's 12 bits. Page table index. Wait a sec, what? No, page offset. Yeah, FFF, yeah. Okay, I kind of wrote my own macros. That was like a little bit less exciting maybe than I thought it could be. Okay, so page dir index. I'm also taking a bit of a gamble by not masking it here. Why is this squiggly like that? Oh, yeah, because this thing needs to be uint pointer t everywhere. Now let's page table index. You know, it's kind of, I do find it a bit weird to yeah, let's add some underscores. Nice, thanks. Why is that squiggly still? You enter. Okay. Now what? So now we've unpacked this virtual address, and now time to use it. So first, we need to get the page directory entry. Page directory entry equals page dir plus dir entry index. Yeah, making full use of like the C, pointer arithmetic. Now we need to, now we need to examine the page directory entry. And just to be like really legit, I'm going to go look it up in the manual. In the hierarchical paging structures part. Paging. Show me at least I'm pretty sure I needed to look up the structure of this in the manual, which is why I ended up here. Okay. But did I already actually copy this over? I think I did. Yep. 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 Okay. So page tables, page directory. Here's how it looks. It's 32 bits long. The high 32 bits are, wait a sec, what? The address of the page table. Okay, here's where my knowledge gets very fuzzy. So, is that a virtual address? It's all these. Probably, I would assume. But in truth, I kind of don't really know. Maybe I can look for help or some more information in this. Okay, it's tons of constants in this file. Okay. Oops. Maybe this is important. To construct a linear address. What does this do? Oh, okay, that's, okay, that makes sense. You just shift it all back and construct the thing. Nice. So what am I stuck on? I'm kind of stuck on what to do with this because now I have the page directory entry. And I need to kind of also unpack it or interrogate it a little bit. And using this documentation, but I would like to know physical address. I mean, it's probably page directory comprises, right? Using the physical address of the linear address. Wait, what? Okay, this is kind of a lot of text to read. But I think it's gotta be here. Ah, yeah, okay. Table 4.4, please do tell. I'm going to take a screenshot of this. Might be handy. Format of a 32-bit page directory entry, blah, blah, blah. Bits of physical address. Of the 4 megabyte page referenced by this entry. Wait. No, wait, this is wrong though. I'm not talking, that's a 4 megabyte. I'm not doing 4 megabyte pages. Format of a 32-bit page directory entry that references a page table. That is exactly what I'm doing. Physical address of a 4K aligned page table. Okay, that is the actual specific information I needed. For kilobytes. Every page is 4 kilobytes. And the page directory has 1024 entries, so 4 megabytes. And so let me just kind of like wing this a little bit. So I'm going to try, so I'm trying to, I think ultimately get like, I'm trying to get those bits, and they're going to be physical address. So the type is T, page table PA. Page table PA equals, and then page dir entry, UN pointer T. I kind of forget where I need. So it's literally just top 22, no. There's 12 bits, 20 bits or something like that. Because this is 12. 12 plus 20 is 32. I'm pretty sure that's correct. So, 12. Just curious, I kind of would have expected I want to make sure I'm doing this and going down the right track here, because I'm pretty sure like the plan is like, okay, take this page directory entry, get those 12 bits. Those are actually a physical address. And I guess we can already tell if it's 0, it doesn't exist yet. I'm just going to go back and check this thing. It doesn't give very much information though. It really and also this header. PTE adder. what is address and page table or page directory entry? So given a PTE, which is interpreted as a physical address, and then the low 12 bits are zeroed out. Which just, yeah, okay, I think I'm sensing this kind of consistent theme where it's all physical addresses, actually. Okay, let me just, I don't know, I'm just gonna kind of keep trying here. I'm just gonna change the page shift just to start using the constants. Well, maybe there's a better constant. There's all these 12s around here of various kinds. Page shift offset P in a linear. No. Okay, I'm just going to keep this 12 just to make it very clear and explicit what's happening. Okay. So now I believe that's a physical address. And I can do things like if page table PA equals 0. I can start to do some error handling. Okay. If create equals false. Like, what is this false thing? This enum. Interesting. It's like this anonymous enum or something like that. Return null. I think I messed something up. Okay. Okay. So if that thing is 0, we can bail out. Oh, 20-second break. All right, be right back. It's honestly fascinating to see the design choices and inner workings of computers, and it's super well documented. Yeah, at least x86 is very well documented. Okay, but given pager returns a pointer, page table entry, right? Let's just assume it's like, I'm just gonna, some test cases, like assume it exists, like the page table exists, it doesn't exist. Those are the major kind of categories we have. Yeah, okay. So let's just say it exists. Else. So in that case, with this physical address pointer to a page table, which is not 0, which is not 0. And we want to convert it we ultimately want to return a kernel virtual address. I think I could maybe visualize this a bit better. So we have this pointer, but ultimately we need to convert that to a kernel virtual address. And how do we do that? The process for converting a physical address to a kernel address. Getting a little bit confused though, because we could do the trick where we add a kern base, but does that work? Oh wait, yes. I mean, it works in this case. No, wait a sec. I think it really depends. I think, yeah, there's this kind of like semi-obvious thing of like, yeah, just, you know, just add kern base to it. But what if we start allocating things? Because like the page table entries, can be anywhere in physical memory. And for us, just for physical memory is 128 megabytes long, which is, I don't know. I literally don't know. I mean, it's like down. This is totally not to scale, but it's like down here or something like that. 20 megabytes. I'm going to go back and read this. Okay, it was talking about, yeah, in order to do that. K-adder, this is that K-adder thing. But I'm pretty sure I read this earlier, and all it does is, and I'm still a little bit confused why that's a legitimate strategy for taking any physical address and converting it to a kernel address, because physical addresses are basically going to be anywhere here. Oh, but yeah, but also, so we have this 256 megabyte space. Right, that was that thing I said earlier. So I think the implicit assumption, or like behind a lot of that documentation and the way that this kernel is organized, is that our machine has maximum 256 megabytes of physical memory. If we can assume this, we can then map all of physical memory, which is like this kind of like low, low-ish region. We can like map that whole range. It's going to occupy, like in our case, like half of this like high area. These diagrams are so hard to understand because they're not to scale. They're like so not to scale. But it's going to like, we can fit all of physical memory in this like top half of the rectangle, which I think therefore makes it pretty trivial. We never need to worry about a physical address exceeding our kernel's virtual memory range. And so therefore, okay, I think I got it now. So therefore, Anyway, this kadder page table. Wow, what all this documentation pops up. Okay. Void page table VA. And we can even go a step further and cast it to the page table entry type, I think. And at this point, we can, okay, I also kind of want to make a return variable, pte p ret equals null, and just do return ret ret equals null. Yeah, again, I'll probably change all this naming later, but that's usually what I do towards the end after I have something that's kind of working. So I'm just doing the happy case now. Let's say we look up the page table physical address. It's not 0, which means that we can then, which means that there is a page table that exists already. We get its virtual address with this macro, and then the final thing we do, I think, is we do ret equals page table VA plus page. Oh wait, what? Dir. This is super weird that this is not right. Yeah. Wait, no, was it? Wait. Dir entry index dir. So easy to get confused. So this thing is the index into this thing. This thing is the index into this thing. Yes, so now we have dir entry index. It's page table index. And we can even just use this down here to make it a bit more local. Page table index. Why? I don't want this massive documentation thing to pop up. Or why? Like, that was kind of annoying. Okay. What? Okay. And no, but that's not correct. That's just, wait, is that correct? I'm just gonna pte page table entry. Yeah, when I start out, when I kind of am doing this initial coding, I always make it kind of verbose with separate variables for every single thing, even if it's not totally necessary, and then maybe compress it a little bit later. Okay. So it's like the happy path page table exists. Then there's the unhappy path that doesn't exist, and then we either have create or not, right? Okay. So here we were like, okay, the page table physical address is 0, therefore it doesn't exist. And if I'm just gonna do a go to fail, actually, return null, because I kind of do fail. Yeah, I don't want to. I could have added an else there too, but I don't know. In some cases, I kind of just prefer to go to a fail label. What is happening here? Do I have a syntax error? Oh, maybe I should compile it. I haven't compiled in a while. Oh wait, it's just fail. Okay. Yeah, so now like what I kind of like is that like I just immediately like bail out of all the logic if I have if I detect that it's not allocated but we're also not creating it, I can just end it and have a very clean sense of what's going to happen, and then I can just nicely have my code for the other case. And so if create is true, then we need to allocate some stuff. Otherwise, allocate a new page table with page alloc. And it's going to be a struct page in, or what? What does page alloc return again? Yeah, struct page info, new page, equal to page alloc, and it should be the page is cleared. Page is cleared. Page walk returns a pointer into the new page table page. Alloc, and I probably want to do alloc 0 here. So now we have this new page, but if page equals null, go to fail, right? So page table physical address was 0, so it means I guess it didn't exist. So, and create is true, so we are creating. We tried to alloc some memory, but it didn't work. Too bad. Go to fail. Otherwise, the new page's ref count is incremented. Okay, new page. Increment the ref count. And page walk returns a pointer into this thing. So this whole thing is going to be this totally cleared out page table. And I see. So this thing actually I think needs to be higher. It needs to be used by both. Yeah. After this code works, we can polish this and make sure the scopes are like tighter and variables are like defined closer to where they are used, stuff like that. But for the moment, I'm not going to do that. Page table index. So now I have this fresh page, and I need to point. I need to get its physical address. Address T, new page, PA. Was it P adder? Page to PA. Right, we've done this before. Page to PA. New page. And then now I need to, like, so we just did, so now in this case, it's the unhappy path where we're like, okay, get the index, check this entry. Oh no, it has a null pointer for this pointer. So now we just allocated a new page table. And then now the next thing we need to do is point that pointer at the page table. And I need to like write to the page directory entry here. And I just do that. I need to make a new entry and then write it to this thing, I think. So page directory entry. So here I'm copying that. Yeah. Okay, so now I want to craft, I want to basically make a copy of the pointer. It's not a pointer though, is it? It's just int32t page dir entry. Oh no, there's already a macro for this. It's like a pt2 page dir entry, new page dir entry, which is basically going, I think it's going to be the same thing as the old. I mean, it's going to be the page dir entry. That's this pointer. Yeah, so we're going to read that out and make the new page dir. And then now I'm going to want to I want to take I already have this thing, which is a 32-bit thing. Okay, real quick. So all these pages are going to be 4K aligned, meaning the 12 low bits are always going to be 0 for these addresses. It's from the page allocator. And I'm trying to assign this thing into this field. So it's going to be something like new page dir. Or equals, and it's going to be like new page, 20-second break, all right. Really coming down to the wire here because I need to go soon, but I would love to kind of at least sort of finish this, even if I can't tell if it works. Okay, new page dir, and then new page PA. I actually think that's kind of it. Because we have this copy. Maybe I'll name this like page dir copy. So we have this copy of the page dir. It's the page dir entry copy. It's the page dir entry copy. And we're just trying to add some more data to it. Fill out the adder and maybe even permissions of pt2. And so we're ORing in the bits of, we have a physical address, which is like this whole, it's a 32-bit thing. It's guaranteed that these are all zeros, basically. To be safe, we could or those out. Also, we could also use an assertion. For example, like assert that new page PA. Probably like a lot of assertions would be very helpful for me for this code right now. I want to assert that if you get the low 12 bits, that's going to be 0. Something like that. PA. This new, because we have this 32-bit thing. It's a pointer. It should be a page aligned pointer. And therefore, yeah, I mean, this is literally the thing that guarantees it. So is there an easier way to do this? I just wanted to confirm, I want to assert that the lower bits are 0. And I'm pretty sure that is what it's going to do. Which means I don't need anything there to maybe fill out other pt2 bits, like permissions, for example. So if we wanted to really do that, we could set some of these bits. But we don't know how the page is going to be used yet. So like it says, so it's safe, meaning it's safe to leave them like and not touch them. So there's actually no to do here. We cannot make any judgment call on that at this point. And then now, man, I think I'm doing this right. So then we need to page dir entry copy. So now we so we took this, we went here, we got the entry, we observed, oh man, the high 12 bits are 0, meaning this thing points to nothing. So then we are creating, and then we allocate a new block of 4K, which just 8 times 512, 4K? Yeah, because there's 512 entries, each are 8 bytes long. Wait, is that right? Wait a second, is that right? They're not 8 bytes long, they're 32 bytes long. But we allocated a 4K. I just got a little bit like weirdly confused by how big. So we allocate, how big is the page table though? 10 bits. I think I did this earlier. 1024. It was 1024 entries. Yeah, 4 bytes times 1024 is 4K. So there's actually 4. I think 512 is on 64-bit or something like that. I kind of forget. Anyway, to really trace it through though, so we ask, like, okay, please, another block of memory, please, we get it. We're like, okay, is it null? We fail. So it's not null. So we actually do have some memory reserved for us. We bump the ref count. We then locate the physical address of this thing, which we need to set the pointer to. And then we make a copy. So I'm going to actually reorder things to clear it up. So we get the physical address of this thing. We then make a copy of the page directory entry. We OR in this physical thing into those bits to set these bits in our local copy, and then we assign it and truly like write it back into this memory and set the pointer, which now points over here. And then we need to finish. And then to finish this off, we need to get this virtual address of page2 kva. It takes a page, yeah. We need to take the, okay, which is a pt2 new page table va, and then we do something very similar. Page table va. In fact, oh, we could even whatever. We could like extract that out or something, but I kind of just don't want to touch it right now. I'm just gonna say, I'm just gonna do the same thing. Page table entry equals. It's not new page VA. It's new page table VA. Page table VA. Page table index ret equals page table entry. Man, okay, I think I'm done. That was definitely, I think, the most hardcore coding I've ever done on this stream. Like in terms of really like deeply OS dev like coding. I don't know if it works, but I have high hopes for it. Yeah. All right, okay. So I'm gonna slowly bring the stream to an end. I'm just gonna plug myself a little bit. Thanks a lot for watching. I'm gonna post my Discord. Feel free to join my Discord if you would like to. It's pretty small and pretty casual. Yeah, I'm gonna end the stream now, but next week, I will actually test this code and keep going with it. But I'm feeling like pretty good about it, but I hope I was right about this understanding that these fields are physical addresses. Well, that is kind of what it says. So, I mean, let's just end with like a build. Does a build? Okay. Oh, wait, what? Error. Oh, so it's suggested parentheses. Like this, you mean? Is that what it? Okay, and it builds. At least it builds. At least I kind of got it. At least it was pretty much building on the first try. Yeah, all right, cool. I'm gonna end the stream. Thanks very much for watching. And I do this every week. Like, comment, and subscribe, blah, 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 blah. And I'll see you next time. Bye.